the science for which you all have assembled. You have decided to devote your one day. I'll be talking mostly on the compound dry hot extremes. Compound dry hot extremes are becoming the new normal now. What is that, and why they are important to be studied? Let's see. I'll be taking around 20 to 25 minutes, and then we can have a question and answer round, whatever the queries, and then followed by this, we will have the hands-on after one more. So let me acknowledge Ravi Kumar Kuntu, who did the primary analysis under my supervision, and Bruno Merz was his Dart mentor from Potsdam when he got the Dart fellowship. So going ahead. This is the outline of my today's talk. I'll be talking briefly on the compound dry hot extreme, the introduction, what is that, why they are important, why should be studied, and then once we are convinced they need to be studied, then we need to understand their characteristics, their spatial extent, for example, their likelihood, and who derives them, why do they occur. So going further, extremes, if we want to understand in a nutshell, the very basic. Sun is the constant source of energy, right? We receive energy from the sun, and this energy comes in the shortwave radiation. And our atmosphere, plays a dual role, right? It's allow the shortwave radiation to come in. The radiation heats up the ground surface. The outgoing terrestrial long wave radiation is impeded or stopped by the atmosphere. Now, with the fueling of more carbon dioxide, with the urbanization, with the industrialization, with the deforestation, we are fueling more carbon dioxide. These carbon dioxide, which is the GHG, which is the greenhouse gases, impede or absorb the long wave radiation, and hence the temperature in the atmosphere increases. If the temperature increases, the atmosphere has the more capacity to hold the water. So that means there is a more moisture, and this moisture now comes at once. So let's say in 30 years back, we were receiving 300 mm rainfall in a January or let's say June month. Still, it's more or less same. But this 300 mm, which used to come in 10 days, now it's coming in one time and together, and that caused the extreme. And we have the very nice explanation. We have the confidence in it why this is happening. So this positive radiation feedback basically causing the changes in the rainfall seasonality, rainfall patterns, temporal patterns, spatial patterns. And because of this, the consequences are there's extremes, and extremes are rising not only in the frequency, not only in the magnitude, in their severity, it's increasing. The IPCC report, the Intergovernmental Panel Climate Change Report 2013 very clearly states that these extremes are connected. These are very much connected. If these are connected, then our studies, our analysis on the univariate extreme, or let's say analyzing one extreme, is good. It has contributed a lot, but is underestimate the risk. It underestimate the disaster. It underestimate the vulnerability we are accounted for. So our framework is not sufficient to characterize the impact of compound events. So how do we define compound events? So officially, the IPCC report very clearly says that the compound extremes are defined as the combination of multiple drivers or hazards that contributes to increased societal or environmental risk. For example, at the same time there is a flood, at the same time there is a drought. The same time there is a flood, there is a heat wave. So we are now we are now exposed to two different hazard or two different disaster together. That's really very much challenging to account for. For example, if I want to show you the type of the compound extremes, it could be the concurrent extreme. Concurrent extreme means two extremes are occurring together. For example, India had witnessed compound drought. We had the drought and hot together during 1957, 1972, 1979, 2002, 9 and 14 and going on. This is called concurrent extreme. The same place at the same time, two different disaster or hazards are occurring together. Temporally, in times, two things are, for example, Kedarnath event. 15, 16, 17 June, there was an extreme rainfall triggering the disastrous event in the history of the India on 17 June. So this is like temporally, they are connected. Or especially like two events are occurring at a geographically separated region. For example, the very much 2000 Pakistan flooding and Russian heat wave. They were very much connected together. It is known as the spatial compound extremes. So these compound extremes now demands our attention. They are more disastrous, and their impacts has to be accounted for. And but the question comes: why should I study? Why should I care for the characteristics and driving mechanism? Because we have they have a crucial implication on our daily life, on agriculture, because India is dominated by agriculture. About 65% of Indian population are directly or indirectly depend on agriculture. Agriculture is a major contribution to our GDP, and Indian southern monsoon precipitation is a crucial for agriculture activities. If these compound extreme changes, it is very much pertinent that our food security, our water security will be under threat. Our question. So this is very much important. So it is not like we are the first one to investigate. Let's recognize the other researchers who have worked on it. For example, multitude of studies have investigated the characteristics, their causes, the prediction, and future prediction of compound dry hot extreme. When I say dry hot extreme, means I'm talking about drought and heat wave occurring together. However, all these studied, when we did the literature review, when we understood what has been done, all these studies were focused on the three hottest month period, which is March, April, May. None of them was focusing on June, July, August, September, which is rather much more important for us because India is agriculture dominated country. Only two studies, our literature says, have concentrated on the ISM, that is June, July, August, September. One was by the Mishra et al. And by Mazumdar. They focused on the JJAS to understand. However, they were focusing on the seasonal scale. What do seasonal scale? For example, JJAS at together. Whether in 2013 in the seasons, in the monsoon, was there compound dry hot extreme. But the intra-seasonality of such an extreme is the paramount. They are very much important. For example, this is our analysis, we are showing in 2002, indeed, there was a compound dry hot extreme. Means the drought and heat wave was occurring together. There was a billions of the loss, loss of the life, everything. But was not equally spreaded in all part of the country, and also not in the June, July, August, September. For example, the influence was much higher in July 2022, not in the September. So the intra-seasonally has to be accounted if we want to really understand their impact, because India is quite complex and quite vast. So we started our analysis, and how we did it. The very first analysis, we used the simple the percentile approach. We defined compound dry hot extreme. For example, the drought or the dry condition, which is the lesser than 25 percentile of rainfall, when the rainfall is less than 25 percentile and the temperature is higher than 75 percentile, how many cases such are occurring in particular all the years. And then we defined the frequency, because we took the entire data from 1977 to 2019, and we compared with the base period 1957 to 2076. Why we divided 2076? Because 76 is considered as the climate shift time, where the exact climate change has been seen. And why? Because this was a time when we saw the very much changes in the Pacific, which triggered the El Nino. So 1976 has been considered as a climate shift period, and we wanted to check how much things have changed comparatively to the base period and how things are evolving. And you'll be surprised to see that almost threefold rise we have seen in the compound dry hot extreme, which we were not really looking at. So how we divided, like the frequency per decade, how many number of events has occurred together, the drought and heat, and the results very clearly says there's a threefold rise in the current time compared to the base time. And the patterns, for example, this is the pattern in the June. We are doing the intra-seasonality for June. If we see the compound dry hot extreme, which are much more focused in the northeast part. If you look at the July, which is much more focused on the southern part of India, the August, which is in the northern part, and the central part, which is and September, you see the central part. The August is rather more challenging, because this is the food belt of India, which India depends majorly or heavily on the food security. If this is the situation in the August, we will also discuss why do we see such a spatial pattern and temporal pattern in each year, which will come back. But this is very much supported by the decreasing and increasing pattern of precipitation temperature. If you ask me, if you look the June, the very first column in the June, we see the compound dry hot extremes are very much rising in the northeast part of India. And this is very much supported by, if you see, the decreasing precipitation and increasing temperature. And this decreasing precipitation is because of the delay of the monsoon. Majorly, we have seen the delay of the monsoon cause the precipitation decreases and the temperature increase in this area, and that's the one of the major factor. In July, if you see, the temperature is increasing and the precipitation is decreasing, and this is majorly because of the aerosol activity, which plays a major role in increasing the temperature. In August, one of the very much concerned reason why which we have done a lot of analysis on the central belt, because this region is very much prominent or pertinent for the food security of India. The major food is come from this region, and this has also very much decreased in the precipitation, increase in the temperature. So this justify what we have seen by the statistical analysis, and then we'll go deep. Spatial extent, how we claim that the spatial extent is changing. India is the complex geography. We cannot do the analysis considering India. So what we did, we divided India into the homogeneous regions. Indeed, IMD, Indian Meteorological Department, has defined the standard 6 regions, but these are based on the stationary approach. Now things are changing, so we defined our own based on the extremes, and we end up with these 10 regions. They have their own characteristic, geographical characteristics, their climatological characteristics, and this we published separately in the Journal of Hydrology. Now, using these regions, we checked how the compound dry hot extremes in changing in the space. For example, I'm showing the example for the North Central India, one of the part. You see the pink one in the June, the second is the July, the third is the August, and then September. But this, with the time, this is rather not clear because we cannot see. So what we have plotted for each decade how the number of compound dry hot extreme number is also important, and the space. If you see, the more we move to the 20th century, the recent time, their spatial extent is increasing like anything. And this is the concern. This is the one of the very important concern, because for the food security, water security, and extremes, and the safety. So our infrastructure, everything has to be adapted and it has to be mitigated. So this is the characteristics, the frequency and spatial extent. Now we wanted to check the likelihood whether they are more prone to occur or it was by random, by chance, and how we did it. We use the cupola theory because you have to deal with the probability now. So probability is that the rainfall is less than 20th percentile, means you are talking about a drought condition, water is not there, and temperature is exceeding 80 percentile, means high temperature, means you are talking about the heat wave. Now in the literature, if we look at, people have modeled this using the Frank cupola family. So there are 4 important families by which we do the joint probability or cupola: Frank, Joe, Gumbel, and Clayton. These 4 families, if some of you have the background, these 4 families have their different nature. For example, if the extremes, if you understand the extremes, if the upper tail is only connected, whenever there is a very high flood, there is a high drought, then it is very much well represented by the Joe. When there's a lower dependence, where for example the lower side, for example the less rainfall and less flood, then it is represented by Clayton. And the Frank is capture the overall dependence, the moderate, small, low, high event, all. In the literature, people have used the Frank. We really wanted to check whether the type of dependence, theta, this theta you see, this P and T are well defined. This is the probability of accidents and non-accidents. P is the non-accidents probability, T is the accidents probability, and theta is the type of dependence, which plays a major role. We very much contributed, this is the methodical contribution to the literature. We checked if we use different family to account the dependence, do we get a different results, or does it really make a sense? So these are the mathematical contribution. I skip it now, but in the hands-on session, we will go deep down in this. And this LMF you see at the bottom is the likelihood multiplication factor. That means what is the likelihood that the compound dry hot extreme will occur. It is given by the Yashler et al., another researcher, but what we contributed, we checked the dependence. So there are 4 families. The Frank capture the overall dependence in the 2 time series. The Clayton and Gumbel are very good for the upper tail dependence, and Joe is good. Clayton is good for the lower tail dependence, and Gumbel and Joe is good for the upper tail dependence. It's the come from the likelihood approach. And then, for example, this figure says if 0 is a value, that means the likelihood is 0. If two things are dependent, the likelihood they will make a compound event is 0. But as the tau is a dependence, as the tau increases, why the negative? Because we are talking one increasing and one decreasing. So negative, precipitation less, temperature high. So as the negative dependence between precipitation and temperature increases, the likelihood of the event will increase. And this value goes until 3, 4, 5. That depends the length of the time series. For example, how many times compound dry hot extreme can occur in a given time period. In a 30-year or 40-year or 50-year, it's same like we do the written period. So this is the figure, very interesting figure, one of the very key contribution. The very first figure shows the negative dependence between precipitation and temperature. The red color very clearly shows that they are negatively dependent, but which is one of the very key phenomena of monsoon climate, right? But this negative association is increasing, is strengthening. And the second is at what grid point which family dominates. For example, Frank or the Clayton or the Joe, and this we do it using the Bayesian information criteria, and then we multiply to identify the likelihood of compound dry hot extremes in this area in part with part. For example, the first is the June, the second is the July, August, and September. How this likelihood of both the event coming together and causing the disastrous event is there. So how the result look like, and then comes as a researcher the authenticity and the reliability of the results. We run the analysis on different data set, University of Delaware, IMD, bias corrected, Aphrodite, and the pattern was almost same all the time. So this shows the reliability. Now, if you want to understand, this is a very nice figure, and what it says the evolution over time, how the dependence is changing. So just focus on this circle at the bottom in the figure. So if you look at the side plot, the tau is the blue, means the negative dependence is less, but likelihood is high. Why this is happening? Please look at this circle. If you look into this first column, A, B, C, D plot, it is blue, but in the plot H, it is red. The likelihood of compound dry hot extreme is red. Why? Because the figure on the left side shows the nature of dependence is changing. Means earlier the Frank was very much dominant, means overall they were connected, but now the connection is going to the extreme side, means at this location less precipitation, high temperature occurs together now. That means extremes are merging, the upper tail dependence is coming together, and for this we really need a very much family to account for. If you will, because the data science is if you rubbish in, rubbish out, you need to know the basics. If there is upper tail dependence, we cannot go for Frank, we have to go for the Joe or Gumbel, and so accounting for the right family is important, and that shows the compound dry hot extreme. That's how we do the prediction and forecasting. So that was the methodical contribution to understand which family and what is the impact of this. Now I'll take you to the next very important thing, is the driver. Sir, why these events are occurring? Who derives them? Because once we understand who derives them, we can make a forecasting and prediction models. So there could be two drivers. One is the local feedback, the local process. One could be the global process, like the climate oscillations, like the climate or land oscillation, teleconnections coming from Pacific, Antarctic, Arctic. So I'm here now presenting the local feedback. What is happening? We hypothesize that the low precipitation basically trigger the soil moisture deficit, and this soil moisture deficit trigger the high temperature, and this basically trigger the dry hot month, and there is an impact. But if our hypothesis is true, it shall show the same results. So what we have done, we have used the conditional precursor coincidence rate. This is the mathematical formula. Just to understand simply, this bracket, the very first shows this mathematical terms quantify how many soil extremes are occurring together with the dry extreme. Whenever there's a low rainfall, how many times there's a low soil moisture. And the upper quantify if this is true that low soil moisture triggered by the low precipitation, how many times it triggered the high temperature. So this is a hypothesis, and we want to check with our data this is true. Then this is a very nice result. The very first figure shows that number of hot extremes in constant with the low precipitation extremes, and the second figure shows this precondition, that the number of hot extreme precondition to the soil moisture deficit preconditioned by low precipitation, and then both the hubs are in very much concurrent. Means whenever this is a local feedback, there'll be extremes, there'll be compound extreme. But what is the process? So now I explain you, this is what we have seen very recently in March and April, May, when the western disturbances were delayed, there was no rainfall, low precipitation, there is a means, there is a soil moisture is dry. If the soil moisture is dry, it will absorb less temperature, less heat, less heat, because the dry soil absorb less heat comparatively to the wet soil. If there is a less soil, the soil is dry, it will absorb less heat, means that temperature will rise. Less, if soil is dry, means there will be less evaporation. Similarly, less water will available for evapotranspiration. So this evapotranspiration decreases, evaporation decreases, soil cannot absorb heat, means the temperature rises. This is like conversion of the sensible heat to the latent heat, and the temperature rises. Then further the high temperature triggers the further decreases the evaporation, further decreases, and this is a closed cycle. And this is what triggers the compound dry hydroxide stream. So the moment we understand that precipitation is less, soil moisture is dry, there'll be compound extremes, and this compound has the very much impact than the univariate extreme. So the take home message, I'll close it. We have done the further analysis, but I close it here. So our study find a widespread threefold rise in the compound dry hot extreme, which is very much disastrous than the univariate extreme. The likelihood of CDHE, which is a compound dry hot extremes in India, depends strongly on the strength, the negative association, and type of dependence, whether they are upper tail dependence, lower tail, or overall dependence. And low soil moisture preconditioned by dry extremes contribute to CDHE occurrence and its spatial diversity. And this is to be continued further. Thank you very much for your kind attention.